Hi guys, today we're going to talk about exponential functions with rates or percentages. Okay, now an exponential function is written as y equals a times b to the x power. Now your a is always going to be your y-intercept. That's going to be your start value. So if we're talking about a savings account or a loan of some sort, that's going to be your principal. Okay, so your starting value or your principal value. Now the b, this is your factor, your multiplicative factor that we're using each time. Okay, this is the exponential factor. If we're looking at these one term at a time, then we just keep multiplying by this b value over and over again. If we're looking at this as an equation, you want to find what it's going to be on the 50th term instead of having to go through each one, then you would do this b value to the 50th power. Okay, now this b value does have restrictions on it. A has restrictions. A has to be greater than 1. Anything less than 1, there are issues. Okay, we're in algebra 1 with this video, so a is always going to be greater than 1. Okay, when you get into higher maths, then you can deal with a is less than 1, and there are that's when you get into some of the transformations of an exponential function. But we just don't do that in algebra 1. Okay, so let's get back to our b here. With our b, we can either have a decay, and a decay is indicated when our b is between 0 and 1, or we can have a growth. And a growth is indicated when our b is greater than 1. Okay, now our b cannot actually be 1 or 0. If our b is 0, then the whole thing is just 0. There's no way to make it grow or decay. And if it's 1, then it's just whatever our a value is, because again, it's not growing or decaying at all. Okay, now to get b, when we have a problem that talks about percentages, okay, when you're talking about trying to determine how much your savings account has grown based on the annual percentage rate, or you're trying to figure out how much the carbon has depleted when you're carbon dating some artifact. In order to figure out b, then you have to follow a couple of simple rules. If it's a decay, your b value is going to be 1 minus the rate, and the rate is your percentage. Okay, if it is a growth, your b is going to be 1 plus the rate, or that percentage. Okay, let's take a look at a couple of examples so you can kind of understand where I'm talking about with the rate and the percentage, where that comes in. Okay, so if I have $1,000, I'm going to put it in a savings account, and it's going to grow at a rate of 3% each year. We're just talking simple interest. We're not going to break it down, by month right now. We're just talking basic simple interest, 3% each year. Okay, so to write our equation, okay, we've got some basic starter things here. This $1,000, that's our principal. That's our a, our starting value. Now, we don't have a b yet, but the fact that it grows tells me it's a growth, so we're going to be adding. And this 3% right here, this is our rate. But we need to change this 3% to a decimal. So 3% as a decimal is 0.03. Okay. Well, here's where all that's going to fit into the equation. So y equals 1,000 times, remember over here with our b value, both of them said 1 minus or 1 plus, depending on whether it was a growth or a decay. So we're going to have 1, and since it's a plus our 0.03, and all of that is to the x power. So then we want to simplify this. We're just going to add that together. So y equals 1,000 times 1.03 to the x power. Okay. Now I want to look at what's this savings account actually going to look like if it's growing at 3% each year. Okay, assuming I don't pull any out and I don't add any more to it. Okay. So I'm going to set up a little table. X is my number of years. Y is the amount of money in my account. Okay. At 0 years, I have $1,000. That's my starting number. Okay, we know that. Okay. After 1 year, I want to know how much money is going to be in that savings account. Okay. Now, with rates, these are not always easy numbers to multiply. And I realize if you don't have a graphing calculator or a scientific calculator at your disposal, don't worry. If you have your phone or you're at a computer, you have a scientific calculator. Okay. If you go to the calculator that's in your phone or your computer and pull that up, it normally comes up to the standard 4-function calculator. Okay. On the computer, if you come up to where you have the 3 lines next to where it says standard, you can go change it to scientific. And you want to do that because this option right here where it says x to the y power is going to let you do your exponential functions. You can see over on the side here where I've been working some exponential functions, and we're going to just clear those out. Okay. So I'm going to put in my 1,000 times 1.03, and I'm going to do this x to the y power, so to the first power. All right, so this is what my b value is right now, okay, times 1,000. All right, so we're going to have 1,030. And that was my fault. I often forget that the calculator on the computer does not always function exactly like the handheld graphing calculators I'm used to using. So we have to go about multiplying these a slightly different way. Okay. If I'm doing the second one, okay, 1,000 times, and in parentheses, I'm going to put 1.03, close my parentheses, and my x to the y, that's going to be 2. So 1,000 times 1.03 to the second power. After 2 years, I now have $1,060.90. Okay. Let's go ahead and look 4 years out. So at 3 years times 1.03 to the third power, we have $1,092. And it says 0.727. So we're going to round that to the nearest penny because we're talking about money, so 0.73. And then for 4 years, 1,000 times 1.03 to the fourth power, and we get $1,125.51. Okay, so there's your growth. Now, if you don't have a computer, a laptop that you can pull up the calculator on, if you are just using the calculator on your phone, oftentimes if you just turn your phone sideways, okay, so that it is in landscape position, that automatically changes your phone calculator from your basic 4-function calculator to a scientific calculator. And then you can do these calculations there. Now you can do the same calculations just by doing 1,000 times 1.03, and that gives you that. Let me clear some things here. Okay, we could do 1,000 times 1.03, and we'll get our 1,030. Then we can multiply that again by 0.103, and that gives us the 1,060.90. Okay, so again, if you don't have a scientific calculator, you can't get your phone to change over, that's fine. You could just keep multiplying by your B value, and that gets you to the next step on your table. Okay, now let's look at decay. Okay, let's say we're going to have the same, we'll use kind of same starter type thing. Let's start with 1,000. But this time, let's say it's 1,000 grams. You have 1,000 grams of some object that you're wanting to carbon date. Okay, so there's 1,000 grams of carbon in the object as you know it. Okay, when I talk about carbon dating, when you have archaeologists and paleontologists that are trying to figure out how old something is, they do that by carbon dating. Okay, and so they look at something and say, okay, well, there's this much of it now, and we know carbon decays at a certain rate. Now, offhand, I don't know exactly what that rate is, so we're just going to say 25%. Okay, each decade. And certain molecules will decay at different rates. So whatever molecule it is that this fictional person is checking out, it decays at a rate of 25% each decade. Okay. Now, one thing I did forget up here is that the year is our X value. Okay, so when we come back down to our decay example, the decades are going to be our X value. Okay, so however many decades it's been. Okay, our A value, we're still starting with 1,000. And it's going to decay, which means we're going to subtract this time. We're going to do 1 minus, okay? Instead of 1 plus, we're going to do 1 minus. And our rate, when we change this 25% to a decimal, it's going to be 0.25, okay? So when we go to write our equation, y equals 1,000 times 1 minus 0.25 to the x power, okay? So it's always going to be to the x power. If I want to simplify this equation, I want to simplify that 1 minus 0.25. I'm going to get 0.75. Okay, so here, if we go back and look, our growth, our B was greater than 1. Here, our decay, our B is less than 1, but it's greater than 0. Okay, so let's figure out how much of this substance we have left after a few years. So 0, 1, 2, 3, and 4. Okay, so X again is our decades. Y is going to be the number of grams we have of this substance, okay? So going back to our calculator over here, I know I start out with 1,000 grams. So 1,000 times, and in my parentheses, I'm going to have 0.75 to the first power. Okay, so I have 750 grams left of this substance after 1 decade. Okay, remember a decade is 10 years. Okay, so after 2 decades, 1,000 times 0.75 to the second power. Well, now I have 562.5 grams left of this substance. Okay. After 3 decades, 1,000 times 0.75 to the third power. Now I have 421.875 grams. Okay, if you want to round that to the nearest hundredth, 0.88. Okay, and after 4 decades, okay, 40 years after this, substance has been around, okay, 1,000 times 0.75 to the fourth power is 316.40625 grams. And again, we can round that to the nearest hundredth, then it would be 0.41. Okay. All right. So that's our decay. The value of y is getting smaller as our x gets larger. Our growth, both x and y, get larger at the same time. Now, there are some words you want to look for. So think about if it's a growth, if you're going to do the 1 plus your rate, you're looking for words like grows, increases, inflates, anything that indicates that it's getting bigger, okay? And a decay, where it's 1 minus the rate, that's going to be, again, that it decays, it decreases, it deflates, or anything that indicates that it's getting smaller, okay? All right, guys, you have a great day, and practice some of your exponential functions with rates, right? Bye.